Section 6.11 Isentropic Processes. In this section, we are going to look into isentropic processes for ideal gases. Let's see an isentropic process on a TS diagram and HS diagram. As the state principle describes, for a simple compressible system, two independent intensive properties can fix the state. Let's say we can fix the state at the initial state 1. So let's say this is the initial state 1. If the system undergoes an isentropic process, entropy remains constant. So S1 equals S2. The isentropic process is represented as a vertical line. So state 2 is somewhere on the vertical line. And we need to know one additional property to fix the state at state 2. So this is constant temperature line. Since y-axis is temperature. And this is constant pressure line. On a HS diagram, this is constant pressure line and constant temperature line. Y-axis is enthalpy, so this is constant enthalpy line. So the location of the second state can be determined with one additional property. One additional property such as temperature or pressure can fix the state. Now let's look into isentropic processes for ideal gases. Isentropic means constant entropy. The entropies at the initial and final states are identical. An ideal gas obeys the ideal gas equation. So PV equals RT. P is the absolute pressure, V is the specific volume, R is the gas constant for a specific gas. T is the absolute temperature. So real gases may be approximated as an ideal gas at low pressures and high temperatures. We will often see that air, oxygens, argon, nitrogens, and carbon monoxide and carbon dioxide are assumed to be an ideal gas. The entropy change of an ideal gas is expressed here. For an isentropic process, entropy change is 0. Recall that previously we defined S degree for ideal gases. It denotes the standard entropy, which is a function of temperature only. And the standard entropy can be taken from the thermodynamic tables. Now, what we are going to do is to establish some relations to determine the properties of ideal gases undergoing an isentropic process. We can write the equations for the pressure ratio P2 over P1. So P2 over P1, or solve it for P2, is P1 times exponential of standard entropy, S degree at temperature T2 minus standard entropy S degree at temperature T1 divided by gas constant R. So we use this equation to solve it for pressure at the final state. Let's consider an isentropic process of air from a reference state to a certain state 1. So we have a state, let's say state 0. This is the reference state. And temperature at the reference state is 0 Kelvin. And the pressure is P0. At state 1, temperature T1, pressure P1. So initial temperature is 0 Kelvin. That is the temperature at the reference state. And the air undergoes an isentropic process. So we can write S1 minus S0. It is an isentropic process, so left term drops out. The standard entropy of air at 0 Kelvin is assumed to be 0 kilojoule per kilogram Kelvin, so it drops out. So we can rearrange the equation and solve it for the pressure ratio. P1 over P0. We are going to call this quantity relative pressure, and it is denoted by PR. So the relative pressure is the amount of the exponential of S degree at temperature T1 over gas constant R. The relative pressure is dimensionless. It's pressure over pressure, so it's dimensionless. We can also confirm that the unit of S degree and gas constant R have the same unit. We can express it in general form. For an isentropic process between the two states, state 1 and 2, the actual pressure ratio P2 over P1 can be expressed as this. So this is the general form of relative pressure between the two states. So P2 over P1 can be written as PR2, relative pressure, over PR1, relative pressure at state 1. Relative pressure is a function of temperature only, as the standard entropy S degree is a function of temperature only. The relative pressure is tabulated in table 822. Relative pressure for air can be found in table 822. The first column shows the temperature, and this column shows the relative pressure. And this shows that delta S equals 0. So this table is good for isentropic process only. So let me explain how to use this table. So at a given temperature, we can determine the relative pressure. So if we know the actual pressure ratio, P2 over P1, which is equal to PR2 over PR1. So we determined PR1 and we know the actual pressure ratio. So PR2 is PR1 times P2 over P1. So we determine PR2. Let's say PR2 is here. So we can determine the temperature that corresponds to the relative pressure. So this will be the temperature at the state 2. Note that the relative pressure is defined for air that undergoes an isentropic process. Air is considered as an ideal gas. It follows the ideal gas law, PV equals RT. Using the ideal gas law, the ratio of specific volume can be also defined similarly in terms of relative volumes, VR. Here we have a similar relations for specific volumes. V2 over V1 equals VR2 over VR1. So VR is the relative specific volume. So relative specific volume is also tabulated in table A22. This is relative volume. Relative volume is also a function of temperature only. So at the given temperature, we can determine the relative volume. For an ideal gas, Cp equals Kr over K-1. K is the specific heat ratio, and constant volume specific heat, Cv equals R over K-1. The specific heat ratio, K, can be written Cp over Cv. And when the ideal gas undergoes isentropic process, we can also use the relations Cp natural log T2 over T1 minus R log P2 over P1. Also Cv log T2 over T1 plus R log V2 over V1. So the left hand side, entropy change terms become 0. So using these relations, and we also assume constant specific heat, the following relations may be acquired. So ratio of temperature is expressed as the ratio of pressure or ratio of specific volume. And the ratio of pressure is also expressed as the ratio of specific volume. And this is for isentropic process, constant specific heat, and ideal gas. The equation may be also written in general form. So this equation is equivalent to Tp 1 minus K over K is constant. These equations, T times specific volume raised to the power K-1 is constant. These equations, P times V to the K power is constant. One thing you must be careful when you use the relations is that you should use the absolute temperature and absolute pressure. Example 6.9. Air undergoes an isentropic process from 1 atm, temperature 540 degree Rankine, to a final state where temperature is T2, 1160 degree Rankine. Employing ideal gas model, determine the final pressure P2 in atm. Solve using relative pressure data from table A22E. And we're going to skip B. Part C. Solve the final pressure using a constant specific heat ratio K, evaluated at the mean temperature 850 degree Rankine from table A20E. So air is expanded isentropically. Air can be treated as an ideal gas. The temperature and pressure at the initial state are known. So on a TS diagram, state 1 is here. So pressure, temperature are known. We know that temperature at state 2, which is higher than the temperature at state 1. So state 2 should be somewhere at T2. And we also know that the process is isentropic, which is represented as a vertical line. So state 2 is where the two lines are met. The final pressure is to be determined. First, we are going to use the relative pressure to determine the final pressure. The relative pressure is a function of temperature alone. So P2 over P1 is the actual pressure ratio equals relative pressure ratio. So we solve it for P2, the final pressure. P1 times PR2 over PR1. P1 is 1 atm. The relative pressures are only function of temperature. See table A22E. The first column shows the temperature in Rankine. So at 540 degree Rankine, PR1 is 1.3860. This is PR1. At state 2, temperature 1160 degree Rankine. And PR2 is here. So 21.18 divided by 1.3860. So we determine the final pressure using the relative pressure. Second, we are going to assume constant specific heat. From table A20E, we get the specific heat ratio at the mean temperature. The mean temperature is 850 degree Rankine. And table A20E shows the temperature in the first column in degree Fahrenheit. So we convert Rankine to degree Fahrenheit. It is 390 degree Fahrenheit, which fall between these two temperatures, and K values will be between these two numbers. So we do the interpolations to get K. So K is determined 1.39. So what we know from the problem statement is that temperature at the two states and the initial pressure. So we can use these relations. And the pressure is P1. So we determine the final pressure using the constant specific heat assumption. So compare the two results. They are slightly different, about 0.1% difference. In the second method, we used constant specific heat approximation. In reality, the specific heats vary with temperature. So to acquire the accurate result, it is always suggested to use the thermodynamic table, the first method. Example 610. A rigid, well-insulated tank is filled initially with 5 kg of air at a pressure of 5 bar and a temperature of 500 Kelvin. A leak develops and air slowly escapes until the pressure of the air remaining in the tank is 1 bar. Employing the ideal gas model, determine the amount of mass remaining in the tank and its temperature. We have a rigid tank. The volume of the rigid tank remains constant. The tank is filled with air. Air is an ideal gas. We have the initial mass, pressure, and temperature of the air in the tank. The mass in the final state is to be determined when the pressure decreases to 1 bar. Ideal gas law, PV mRT. The volume is mRT over P. The volume of the rigid tank remains constant. So M1R T1 So V1 equals V2. R cancels out. Solve it for M2. We know the pressure ratio. We know temperature T1. We know mass at the initial condition. So if we find the temperature at the final state, we can determine the mass. This may not be straightforward, but we are going to assume that the air leaks slowly. So it is a reversible and adiabatic process, or it is an isentropic process. So air leaks slowly and the tank is well insulated. No heat transfer occurs during the process. Assuming an isentropic process, the pressure ratios equals relative pressure ratio. And solve it for PR2. PR1 times P2 over P1. At 500 Kelvin, PR1 is here. So 8.411 times 1 bar over 5 bar, which is 1.6822. From the relative pressure at state 2, so 1.6822 falls between these two numbers, which means the temperature is between these two values. So we interpolate to determine the temperature at relative pressure 1.6822. So T2 can be found 317 Kelvin. So going back here, P2 1 bar, 500 Kelvin. So mass of the air at the final state is calculated.